All right, welcome back, everybody. So we're moving on to the end of section 1.3, and we're going to get into section 1.4. Really what we'll do for section 1.4 is a few examples on the blackboard. But for section 1.3, we're completing it by talking about how do we solve systems of nonlinear ODEs. Now, you may recall that the first thing we encountered was the constant coefficient linear ODEs, and I said you can violate that collection of ODEs in two ways. You can either make it non-constant coefficient or you can make it nonlinear. So we already analyzed the non-constant coefficient ODEs. Now we're going to analyze the nonlinear ODEs, and these are pretty tricky objects to solve. In most cases, we can't solve these systems. Classic example of one of these is the Lorentz system and strange attractor. This is that system that creates that funky butterfly looking shape. This is the Lorentz strange attractor, and it's a chaotic system with no elementary solutions, for most initial conditions. So this is a great example of a system of nonlinear ODEs. We will encounter the best possible case in this proposition. So I've introduced this proposition as the best possible case. This is basically the higher dimensional analog to separable equations. You probably encountered separable equations in your ODE course, and they were really easy to solve. You would separate terms in y and terms in your independent variable out, integrate them individually, and then solve the problem. The best we can do for systems, if we have now a vector valued y that we take a derivative of and a vector valued f, which maybe depends on y and depends on time. If this is nonlinear, then the best we can do is try to represent f in the following way. So if we can represent f, the vector valued f, which is just whatever's on the right hand side of the equation, if we can represent that as a gradient in the y variables of a vector valued g, that would be a matrix because the gradient itself is a vector, and we're going to be taking the outer product against a vector valued function. You can think about this as the Jacobian matrix if you want. If you take the inverse of that matrix, add a minus sign, and then act it on the partial derivative in time of this vector valued g. Okay, so we've got a matrix acting on a vector. This is going to give me some vector. If that vector is f, then we can actually solve our system of ODEs. But finding such a g is really often impossible, if not really, really hard. So that's why these problems end up being really, really hard. Is the best we can do is one of these situations, but it's really hard to find such a g. Let's just suppose we have it. Somebody gave it to us. They're omniscient. If somebody gives us a g for which this is true, what can we do? We can actually solve the ODE as the following. Here's our initial conditions. The initial time is t0. The initial vector is y0. I plug those in to g, and I set it equal to g of t and y, where these are not defined. So this is y and t equals g of t naught and y naught. Now this is an implicit solution, right? Because ideally we would want to solve this for y. So an explicit solution exists if we can solve for the vector y. If you manage to solve that equation for the vector y, then you have an explicit solution. I've got a proof there. It's pretty straightforward. But let's actually see an example of this in action. So we've got this system. There's x, there's y. If you take a derivative of x or a derivative of y, you know that the derivative in x has to be equal to this combination of x's, y's, and t's. T is our independent variable. The derivative of y is equal to this combination of x's, y's, and t's. And so this basically looks like it's impossible to solve. Like, how on earth would we actually solve that sort of system of nonlinear ODEs? It seems really tricky. And yet, somebody came by, I don't know who they were, but somebody came by and said, hint, hint, nudge, nudge, this vector valued function of t, x, and y has the property for which if we compute its Jacobian and then an inverse and act that on the partial derivative in time of this vector and add a negative sign, we end up with exactly the right-hand side of the differential equation, right? So this is, the whole x prime thing. This is the whole y prime thing. If I scroll up, that's what you'll see. So somebody came by and they said, hey, I can actually represent the right-hand side as the inverse of a Jacobian times the temporal derivative of a vector field. And I said, great, that's awesome. I will solve the differential equation then. So the differential equation has to be solved by setting g of txy equal to g of t naught x naught y naught, where this is the evaluation at the initial conditions. So you evaluate at the initial conditions, you set it equal to that, and we see that, you know, this is an implicit solution. You know, it's got it basically, by implicit, what do I mean? I mean we have a relationship between x, y, and t. Well, a relationship between x, y, and t, as long as there's enough information here, which there definitely is, we could solve this for just x and y in terms of just t. Now, you can't always do that. Some equations are not solvable. Certainly nonlinear equations are not solvable. I was really surprised when the computer told me it was able to solve this, and I got an answer. And so this one is definitely solvable, surprisingly. And we get the following. And there's exactly an equation for x, right? The definition for x, which solves our equation, so long as y has this definition as well. And so we could leave it in the vector form there. We could, you know, introduce it just as two functions which equally solve the original initial value problem. If you want to go ahead and you know, actually compute derivatives of this and try it out for yourself, you would see that this is definitely a solution. And in fact, there are quite a few solutions here. This is a case of a nonlinear system having non-unique solutions. So this is one of, I believe, 3 different solutions to the system. So you're not going to be asked to do these sorts of problems. They really do require that somebody who's omniscient jumps over and tells you what G is supposed to look like, or I guess it's this section here. Somebody shows up and says, hey, G looks like the following. There's not really a way to solve these problems without somebody doing that for you. And so what we have instead is the one that you encountered in ODEs, and this is the case of separable ODEs. So when you were in ODEs, probably you learned to solve separable ODEs, which looked like the following. They were always first order, and there was always an initial condition because they're first order. And the function on the right-hand side did not look like f of t y necessarily. It had a structure that was prettier than that. Given a better structure, and the way I like to represent this better structure is as a ratio of a function of t to a function of y. Now, you probably were told in ODEs that it was a multiplication of a function in t and a function in y. They're equivalent, right? Because I could consider, you know, phi of t divided by psi of y as phi of t multiplied by 1 divided by psi of y. So there's, you know, there's your multiplication of a function of t with a function of y. But it's equivalent. I like writing it this way for the sole purpose that the solution looks better this way. So you can give a really quick solution formula if you write it as a ratio instead of a multiplication. That solution formula is the following. Solution y is the inverse function of the antiderivative of psi. Okay, so this is the inverse function of the antiderivative of psi. Whatever that was, you find an antiderivative, you calculate its inverse, and then you act that inverse function on phi of t, which capital Phi is the antiderivative of lowercase phi, evaluated at t, plus psi, capital psi, so this is the antiderivative again, at the initial condition, minus capital Phi at the initial condition. And then that's all inside of phi inverse, right? So all of these terms are inside of phi inverse. And so all we need to do to solve separable problems is find an antiderivative of whatever phi is and an antiderivative of whatever psi is and compute psi inverse, right? So there's really 3 steps, which is find antiderivative of phi, find antiderivative of psi, calculate capital psi inverse. And then you can construct everything using the formula. Now, I need to comment on this because too many students make this mistake. This is remark 1.3.17. I do not want any of you making this mistake. If you do, I'll know that you didn't watch this part of the video. An inverse function is not a reciprocal function. A lot of students like to see this power, something to the -1 power, and they immediately assume that it's 1 divided by that thing. That's only true for numbers. -1 power means division only with numbers. Never, I shouldn't say never, but basically never with functions. Okay? So don't interpret in the solution formula that we just covered this solution formula, do not interpret this as dividing. This is not dividing. I don't want to see it as dividing when I'm grading things. This is not going to be dividing. It's something more complicated than that. If it were dividing, I would have written this as a division. You can tell how many students have turned in solutions where they divide by inverse functions to me. I'm only 28 years old and already sick of it. Okay, what is an inverse function then? You should have covered this in probably algebra 2, but it's fine. We can cover it again. The inverse function is the function which inverts itself, right? So if I take a function and I place the inverse inside of, this is important, we put it inside, also known as composition. If we place it inside of my other function, they cancel out and we get x. Or if I place it outside, in the sense of that I put the regular function inside, the inverse function, once again, this is function composition, they cancel out. Okay, so inverse functions are inverses with respect to the operation of composition, not the operation of multiplication. I think you're all going to be good on that now because I spent so much time. All right, so that's the inverse function. We'll go through an example, make sure we know how to do this. So we're going to solve the IVP. Y prime is log t over y squared. And this shouldn't be too bad. We're finding phi, we're finding psi. If phi is log, and psi is y squared, we can immediately find their antiderivatives, capital Phi, as t log t minus t, and y squared goes to capital psi of y, which will be y cubed over 3. Now we have to find psi inverse y. Jumping way back probably to algebra 2, how do we find an inverse function? Well, we set the right hand, or we set one of the sides, right? We're going to set this left-hand side equal to x and solve for y. So we set the left-hand side equal to x, we solve for y. What do we have to do? We have to multiply by 3. We get y cubed is 3x. We have to take a cube root, right? That's how we're going to get rid of a power of 3, is by taking a 1/3 power. So psi inverse is the function, I'll call it psi inverse of x actually. Psi inverse of x is the function 3x to the 1/3 power. Now that we know that, we can construct everything we need. We've got t log t minus t, we've got y cubed over 3, we've got the inverse function. All we do is we grab everything and we make sure we put it in correctly. So this is psi at 0. Let's recall what capital psi is. Capital psi is y cubed over 3. So psi at 0 is 0 cubed over 3, which is 0. We can compute capital Phi of e. Capital Phi was here, t log t minus 1. This is going to be e log e minus 1. Log of e is 1. 1 minus 1 is 0. That's going to be 0. So thankfully, neither of those terms survive. So both of these terms are going to be 0. Phi of t is going to be t log t minus 1. And psi inverse, right? So this needs to go inside of psi inverse. Everything that results here needs to go into psi inverse. If psi inverse is this, if I place something inside of it, I'm replacing x, okay? So every x becomes that, which is where I'm coming out with 3t log t minus 1 to the 1/3 power. So that's going to be the solution to my separable ODE. Moving on to section 1.4, we've got a table of common one-dimensional ODEs and their solutions. I have 2 remarks that I want to cover here before I head over to the blackboard. And that's that we can use Euler's formula with complex exponents. So a lot of times, if I scroll down a little bit here, we're going to see these sorts of exponential e to a power, lambda, and a lot of times these powers are going to be complex valued, okay? So if those powers are complex valued, we have to be a little bit careful about extracting our answers. When we have a complex valued power, e to the x plus iy, this actually becomes e to the x cosine y plus I e to the x sine y. So that's going to be a possibility. And in fact, if I start with real numbers, if everything starts with real numbers, all of these terms will cancel. So we start with real coefficients. We're going to see that all of the imaginary terms cancel when we make this equality. This is called Euler's formula. So that's something we can do if we want to find cosine and sine terms. I shouldn't say all of the sine terms cancel. What I should actually say is that all of the imaginary terms cancel. So there won't be anything imaginary left over if we do things correctly. Second remark is about L'Hopital's rule in the event that we have degenerate frequencies. So there's going to be some situations when this lambda, which I'm calling lambda plus minus, I'm giving it a name as basically the solutions to a quadratic, right? There's your quadratic formula. There's going to be a lot of situations where this b squared minus 4ac is equal to 0, in which case lambda plus equals lambda minus. And what's going to happen here? We're going to have that is 0. B squared minus 4ac is 0, so we've got a 0 in the denominator. Let's look at the numerator. If lambda plus and lambda minus are the same number, then the numerator is also 0. So we're going to end up with a 0 over 0. Must use L'Hopital's rule. So under using L'Hopital's rule, you can actually recover the correct formula here. It's going to be the same here, actually, because both the numerator and the denominator will be 0 over 0. And so you'll have the same sort of behavior. So that's in the event of a degenerate frequency. Frequency because the lambdas can be considered frequencies. So you'll have to use L'Hopital's rule on that formula as well as on this formula here. So you'll notice on this formula, if the lambdas, the lambda plus and the lambda minuses are equal, you will similarly recover 0 over 0s in this formula. Okay, with that said, we're just going to move on to the blackboard and we're going to cover a couple of good examples. Okay, welcome to the blackboard. So we're just going to analyze 3 different fairly straightforward ODEs on the blackboard and make sure that we recall all of our knowledge from our previous course, at least with these ODEs. So first one's going to be maybe the trickiest. This is going to be a system of, it's a constant coefficient system, but a system of 2 ODEs. So obviously with 2 unknowns. This is going to be y1 prime equals 2y1 plus 8y2. And then we have y2 prime is negative y1 minus 2y2. We have that y1 at 0 is 2, and y2 at 0 is negative 1. Now, unfortunately, the solution to this is not given on section 1.4, where we have a table, because this is a system in 2 dimensions. We have both y1 and y2 as our dimensions. And so we need to recall either back to the matrix exponential or to our ODEs course, however we decided to learn this, how to solve equations like this. So let's do 2 ways of solving. I'm going to call it the traditional way, and then the matrix exponential, which is really the way that should be traditional, but it's a little trickier if you don't know linear algebra very well. So let's go with the traditional way. Solution is given by y is a vector, so this vector is going to be the vector of y1 and y2. And it equals c1 times an eigenvector, and we call the eigenvector x with an arrow over it because it's a vector, corresponding to an eigenvalue lambda, so I'm going to call that lambda 1 is my first eigenvalue, e to the lambda 1 t plus c2 eigenvector corresponding to lambda 2 e to the lambda 2 t, where lambda 1, lambda 2 are the eigenvalues of the matrix M. Where's my matrix here? Let's see if we can find it. Coefficient, 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 coefficient. My matrix comes from the coefficients. It's going to be 2, 8, negative 1, negative 2, and x, lambda 1, x, lambda 2 are their corresponding eigenvectors. So I'm going to solve it, and then I'm going to have to find C1 and C2 to satisfy the initial conditions. Let's go ahead and find those eigenvalues. It's probably been a while. So to find eigenvalues, we start with the characteristic equation. Which is going to be the determinant of M minus lambda times the identity is equal to 0. Or I could write this as the determinant of the matrix. There's M, 2, 8, negative 1, negative 2. And if I subtract lambda times the identity, that's subtracting lambda along the diagonals. The determinant of a 2 by 2 matrix is not too hard. It's AD minus BC. And so we end up with 2 minus lambda, negative 2 minus lambda. That's the A and the D, or the downward diagonal, minus the multiplication of the upward diagonal, negative 1 times 8. We end up with, if I FOIL, negative 4. Outside gives me minus 2 lambda. The inside gives me plus 2 lambda. And the last gives me plus lambda squared. Then I've got plus 8 sitting around. Okay, so minus 2 lambda plus 2 lambda cancel. Negative 4 plus 8 gives me a positive 4. Lambda squared plus 4 is my determinant. If it's the characteristic equation, I set that equal to 0. And now I need to solve for lambda. And we're going to recover that lambda 1 is 2i, lambda 2 is negative 2i. So unfortunately, we do have complex valued solutions here, but that's not the end of the world. If we want to find eigenvectors, we need to choose, maybe lambda 1 first, and write 2 minus lambda 1, 8, negative 1, negative 2, minus lambda 1 against x1, x2 equals 0, 0. If I actually compute this multiplication, what do I recover? I get 2 minus lambda 1, x1 plus 8, x2 is 0. That's the first row that I get when I compute that. The second row gives me negative x1 minus, let's say plus, negative 2 minus lambda 1, x2 is 0. Now lambda 1, you'll recall, is 2i, so I could rewrite this as, let's rewrite it, 2, 1 minus I, x1, and I could rewrite this as negative 2, 1 plus I, x2. Now when it comes to eigenvectors, all we need is a relationship. So either one of these two will give me the relationship. This gives me a relationship between x1 and x2. What is the relationship this gives me? Well, I could just solve it for x1. It says that x1, I'm going to move x1 to the right-hand side to solve that for x1. It says x1 is negative 2, 1 plus I, x2. And I can make the choice that x2 is 1, so that x1 is negative 2, 1 plus I. Okay, so that's my x1 and my x2. So that means that my original eigenvector that goes in here, x1 is negative 2, 1 plus I, x2 is 1. I'm just using these values right here. All right, so that means that my first eigenvector is going to be negative 2 times 1 plus I, and 1. So let's write that down. x1, negative 2, 1 plus I, and 1. x2, because everything is real valued in my original ODE, x2 has to be the complex conjugate, which means all I do is I'm changing the plus sign here to a minus sign there. And now I have my eigenvectors. My eigenvalues were lambda 1 is 2i, lambda 2 is negative 2i. You can see that those were also complex conjugates of one another. So jumping up to the solution formula, we have everything we need. The solution is given by y of t is c1 times the first eigenvector, negative 2, 1 plus I, 1, e to the eigenvalue, 2 plus I t, plus c2, negative 2, 1 minus I, 1, e to the negative 2I t. That's all fun and games until we have to meet the initial conditions So to meet the initial conditions, we actually have to evaluate at 0. So at t equals 0, we have y0 equals c1, 2 times 1 plus I, 1. E to the 0 power will always be 0, and I've got c2, negative 2, 1 minus I, 1. And then once again, e to the 0 is still 1. So this needs to meet the initial conditions, 2, negative 1. So I've got that this has to be equal to 2, negative 1. I'm going to try to solve this system of equations. Solving this system of equations isn't that bad. Let's use the bottom row first. So the bottom row says c1 plus c2 is negative 1. The top row says 2 times 1 plus I c1 minus 2 times 1 minus I c2 is 2. I can make my life really easy by dividing everything by 2. And the first case, I can solve that c1 is negative 1 minus c2. And so I grab that whole term, plug it in for c1, and get 1 plus I times negative 1 minus c2 minus 1 minus I c2 is, that was supposed to be equal to 1. And then I'm going to add everything together, FOIL, and then add everything together. So let's FOIL. What do we get? We get negative 1 minus I minus c2 minus I c2 minus c2 plus I c2 equals 1. If we cancel some terms that cancel, it looks like I have c2, negative 2c2, because there's 1, 2 of those. I'm going to bring these terms to the right. I've got 2 plus I, or in other words, c2 is 1 plus I over 2. c2, replace that with 1 plus I over 2. c1, we decided satisfied this equation. And so if I take 1 and subtract c2 here, I get negative I over 2. Okay, so that means that the true solution to this ODE, do my best to grab everything. True solution is going to be y1 true solution is going to be the vector y is negative I over 2, negative 2, 1 plus I, 1, e to the 2it, plus 1 plus I over 2, negative 2, 1 minus I, 1, e to the negative 2it. So there's the actual solution. If you wanted this, only real solutions, use Euler's formula and expand e to the 2i t by Euler's formula is cosine of 2t plus I sine of 2t. So both of those exponentials can turn into those sorts of cosines and sines. Expand everything out, you'll notice all the i's cancel, and you get the actual solution, which is a real solution. So that's one way of solving it. The matrix exponential way I won't get into today because we're running out of time, but I'll move forward to the next problem we're going to solve. Okay, let's move on to the second example problem for today. This is a second order linear constant coefficients problem, y double prime minus 2y prime plus 2y equals 0. And it's a boundary value problem, so we've got y at pi over 2 should be 0, and y at pi should be negative 1. We're going to solve this problem. You could look at section 1.4 if you wanted to, compute lambda plus minus from a, b, and c, and so on. We're going to solve this problem actually more similar to how you maybe learned in your ODEs course, and that's with the characteristic equation. Setting up, replacing each of the y's with powers of lambda. So we end up with lambda squared minus 2 lambda plus 2 equals 0. There's actually a lambda to the 0th power by the 2 there. That's why you don't see it, because to the 0th power is 1. We're going to solve this. for lambda. And when we solve it for lambda, we're just using the quadratic formula. We get 2 plus or minus the square root of negative 2 squared, which is 4, minus 4ac, which will be 8, all divided by 2a, which is 2. And I'm going to give this the name lambda plus minus. When I give these the name lambda plus minus, I'm referring to whether or not I'm using the positive or the negative, positive or negative square root when I'm adding in the middle of my quadratic equation. Well, if we simplify this a little bit more, the 2 here can distribute to both terms there and there. We end up with, I mean, it gets squared when it comes under the square root, but we end up with 1 plus or minus the square root. That was negative 4. It's being divided by 2 squared. Negative 4 divided by 2 squared is negative 1. Square root of negative 1 is I. We have 1 plus or minus I. So that's going to be lambda plus minus here. And our solutions are going to be given by C1 e to the, we're looking at the real part of lambda plus, and then we're going to end up with cosine the imaginary part of lambda. It's going to be t. We're going to have C2 e to the real part lambda. It doesn't matter if you choose lambda plus or minus actually on these, but real part t sine the imaginary part of lambda. Sure, we'll choose minus t. There should be t in here as well. Okay, so we just need to identify the real and the imaginary parts here. The real part is 1. The imaginary part is the coefficient on I. It's not the I itself, but the coefficient on I is also 1. So that means our solutions take the form C1 e to the t cosine t plus C2 e to the t sine t. All right, now we need to meet our boundary conditions. Let's see if we can do that. So to meet those, we're going to evaluate. So let's evaluate y at pi over 2. Keep in mind pi over 2 is where on the unit circle? I've moved, there's pi. If I ended up there, it's pi. So pi over 2 must be up here. This is where cosine is 0 and sine is 1. Cosine 0, sine is 1. So the 0 term drops out. I've got C2 e to the pi over 2, sine is 1. This has to be equal to 0. That immediately tells me C2 is 0. If I look at y at pi, now I've moved all the way around the unit circle. Cosine is 1, sine is 0. So I get C1 e to the pi, cosine is 1, sine is 0, this is negative 1. I end up that C1 is negative e to the negative pi. So that gives me my solution. Once I replace these, right, so C1 is given there, C2 is 0. I'm just going to put those in. It's negative e to the minus pi, and then that's going to multiply the e to the t. So I'm going to write this actually as t minus pi cosine t. It's the solution to this boundary value problem. The third problem we're going to have a look at is a nonlinear problem, second order nonlinear problem. X prime times x double prime equals 4t. X at t equals 1 is 5, and x prime at t equals 1 is 2. This is a nonlinear problem because we have this multiplication here. Moreover, we actually have a second order nonlinear problem that's missing any 0th order term, so that's very interesting. But let's think about it. Let's think about maybe what we could do to make our lives a little bit easier to try to solve just the ODE itself. Let's give x prime the name y. If we give x prime the name y, then in fact, then x double prime is just y prime. And we can rewrite our equation as y times y prime is 4t. Or in other words, y prime is 4t divided by y. All of a sudden this looks like a separable problem, right? We've got a numerator and a denominator. The numerator only cares about time. The denominator only cares about my variable. And so I can find the antiderivative of 4t, which is going to be 4t squared over 2, also known as 2t squared. I can find the antiderivative of y, which is also known as y squared over 2. This is going to be capital psi. This is going to be capital phi. And in the first order equation, right, so x prime is my variable I'm looking at, so that's actually the initial condition of the first order equation. In the first order equation, I now have a solution, y of t equals, this is my initial condition, so that's t0, that's y0. It's going to be psi inverse of phi of t, capital Phi, minus psi at the initial condition plus phi at the initial condition. Okay, so what do I need? I need psi inverse, and I have the rest of my values here. Okay, so psi inverse, we're going to extract that right here by calling this x and solving for y. If that's x and I solve for y, I have to multiply by 2 and take a square root. I get that y is square root 2x. And so this psi inverse is the square root of 2 times whatever the rest of this is. Well, I know that capital phi is 2t squared plus psi at the initial condition. There's psi, y squared over 2. The initial y value is 2, so that's 4 divided by 2. 4 divided by 2 is 2, minus phi at the initial condition. Phi is 2t squared. The initial condition is 1 for time. 2 times 1 squared is 2. And so I end up with this, or in other words, square root of 4t squared. Thankfully, everything is a square here, and I end up with 2t. All right, so that means y is 2t, but that's not what I was looking for. I was looking for x. We gave x prime the name y, so in fact, x prime of t is 2t. What does that make x? Well, we just have to take an integral now. Now we know what the derivative is equal to. We take an integral, and what do we get? We get that x is t squared over 2 times 2, so we get t squared, plus some constant, because an antiderivative is only unique up to a constant, and we can find that constant by evaluating at our other initial condition, which is x at 1 has to be equal to 5. At 1, this is 1 squared plus c, so c has to be 4. We recover x is going to be t squared plus 4. There you go. That's how you solve 3 examples of some fairly straightforward ODEs. I'll see you in the next class. Bye.